Okay, so transients and steady states. And so we'll define what these are. Transients, a transient is something that lasts for a very brief time. So that's what a transient is. So we'll define it and do some examples, and we'll talk about the solution a little bit. So what we have is sometimes we have a damped spring, right? A spring with friction, right? So P is not equal to 0. And we'll force it with a periodic force. So we apply a force that oscillates, and it forces the spring. It drives the frame. It drives the mass on the spring. And we'll only consider cosine terms for simplicity. You can't deal with sine terms with trig identities. So this is the forced equation. Y double prime plus py prime plus qy. This is our spring. And then this is the forcing function, cosine eta of t. This is the Greek letter eta. And that's the forcing frequency. So we have something pushing this at a particular frequency of eta, and then we have y double prime plus py prime plus qy is the left-hand side. And the solution to such an equation, right, is homogeneous solution plus the particular solution. The homogeneous solution is going to turn out to be called the transient, and the particular solution will be called the steady state solution. We'll see why those names are appropriate when we get to these examples. So here's a initial value problem, sketch its solution, check it on GeoGebra, and when does the homogeneous solution get less than about 0.001? So find y sub h of t, r squared plus 5r plus 6r equals 0 is our characteristic equation. R plus 3 times r plus 2 is how it factors. So that gives me my two eigenvalues, -3 and r equals -2. So the homogeneous solution is k1 e to the -3t plus k2 e to the -2t. We make a guess. Yp of t equals, well, since 10 cosine t, we want to guess a cosine t plus b sine t. Then we do the usual thing, find yp prime of t, yp double prime of t, plug into the ODE, right? Plug it into the left side there and solve for A and B. We end up with, find it, A equals 1 and B equals 1. So yp of t is cosine t plus sine t. And as we usually like to do when we have these sorts of things, we want to rewrite it as a single cosine term, a cosine t minus a phase angle. What are the equations for this? Well, the coefficients are 1 times cosine t and 1 times sine t. A squared is the coefficient, sum of the coefficients squared equals 2. So a equals square root of 2. Phi, tangent of phi is the ratio of the coefficient of sine to the coefficient of cosine. So phi equals arctangent of 1, which is pi over 4. So we can write yp of t as square root of 2 cosine of t minus pi over 4. We want to sketch the solution. It's a little bit tricky, but it's not too bad. So y is, 3. Use initial condition to find k1, k2, right? And our initial conditions are these. Plug in t equals 0, right? We're given an initial displacement of 2 and initial velocity of -1. Plug those in, and you can actually get that K1 equals 1 and K2 equals 0. So now to graph it, so what is y? Y is K1 equals 1, so that's e to the minus 3t plus square root of 2 cosine of t minus pi over 4. So what does the graph of that look like? It's a little bit tricky to think about that because it's an addition of two things, but we know e to the minus 3t looks something like that. We know that square root of 2 cosine of t minus pi over 4, this is cosine, shifted to the right by pi over 4, and square root of 2 as its amplitude. So this part, this is y sub h. This whole thing is y sub p. The graph of y sub p looks pretty much like, it's a cosine curve like that. And so the solution curve is these two added together. It should look something like, well, if we add these together, we'll get something up here that comes down. And then by the time we get down to here, the homogeneous solutions actually become pretty small, right? So we're pretty much just following the particular solution. Okay, so we can solve this. We get a homogeneous solution that involves a negative exponential, and we get a particular solution that's a cosine term that's oscillatory. So what does this look like if we go and look at this in GeoGebra? If I can figure out, there it is. Great, so this is the graph of the solution, right? E to the minus 2x, using x instead of t here, square root of 2 cosine x minus pi 4, that's that graph. And so you can see what the solution looks like. There's something a little bit weird here at the beginning, but then it settles down into a nice cosine curve, just oscillating up and down. So what's actually going on here is we can look at, we'll get rid of that, and we'll look at the homogeneous solution. That's just this decaying exponential. And we can look at the particular solution, which is this cosine curve. Okay, so when we add those together, what happens? Well, by the time you get to 2, you can see that t equals 2, you can see that the green curve is pretty much down at 0. And so if we're adding the green curve to the blue curve, once we're past t equals 2, the green curve is 0. It doesn't add anything to this. So if we look at the sum of the two of those, what do we get? Well, there's the solution curve. So by the time we get to 2 equals 2, the red curve, which is our actual solution, is pretty much the same as the blue curve. And why is that? Well, that's because an exponential dies off pretty quickly. So when is e to the minus 2x so small that we can ignore it? Well, we can zoom in a lot and say, okay, when are we actually going to get down to, say, 0.001? 0.001, right? So is that, I think, what we're looking for in here? When is y sub h less than 0.001? I've lost track of where I am. Oh, here we are. Okay, so 0.01 instead of 0.001. So we go out to the right. Exponentials die pretty quickly. So there's that exponential kicking in. Right about 2.3, right? If we actually calculate that, it's about 0.01. It's just an estimate, so we don't need to be too particular about it. So at that point, right, the homogeneous equation is so small that we can essentially ignore it, right? And so if we come back out to reasonable y values, there we go. And we look at our solution, right? Right around here, this is where the homogeneous solutions got so small that we can just ignore it. We can put in this particular solution, right? And that's about where the red curve and the blue curve just start running together. So at about 2.3, we go back to the notes. Where's my notes? I know it's boring to hear me say, where's my notes, but there we go. Actually, we found it less than 0.01. Oh, that's up here. So this is about this happens at about t equals 2.3. Once we get past that, the homogeneous solution is just decayed and is gone, and all we see is the particular solution. Okay, so a similar case here, right? What's the solution to this? What are the two steps? One, find the homogeneous solution, and that's going to be k1 e to the minus 2t cosine t plus k2 e to the minus 2t sine t, because our characteristic equation is this, and then r equals -2 plus or minus I. We're just assuming that they just to, simplify things a little bit, because we're not really interested in the algebra. We'll just assume that k1 equals 1 and k2 equals 0, so that our homogeneous solution is e to the minus 2t cosine t. So this is an underdamped system because we've got a complex eigenvalue, but the negative exponential again is going to force the solution, the homogeneous solution, to 0. What's the particular solution that we guess? Well, we guess a cosine 2t plus b sine 2t. You do the usual thing of plugging its derivative and its second derivative into this equation to figure out what a and b are. And we can actually, if we actually do that, a equal to 1 and b equal to 8. So yp of t is equal to cosine 2t plus 8 sine 2t. We do want to rewrite this again. We want to rewrite this as a cosine 2t minus phi, where phi is our phase angle and a is our amplitude. What's a? A squared is the sum of the squares of the coefficients, which are 1 and 8. So a equals square root of 65. Tangent of phi is the ratio of the sine coefficient to the cosine coefficient, which is 8/1. So phi is inverse tangent or arctangent of 8, which is about 1.45 radians, or about 82.87 degrees. Great. So I'll just leave it as arctangent of 8 for now. So the particular solution is square root of 65 cosine of 2t minus arctangent of 8. So our solution is e to the minus 2t cosine t plus square root of 65 cosine of 2t minus arctangent of 8. Great. And this is our homogeneous solution. And this is our particular solution. The homogeneous solution, if you graph these things, as we just sketch this very briefly, e to the minus 2t cosine t is a decaying cosine function. It looks like that, because the e to the minus 2t, that's going to drive it to 0. This is a cosine function with amplitude square root of 65. So this starts at 1. Square root of 65 is about 8. So we get some kind of a cosine function like this for the particular solution. And you see the same thing. After a while, the homogeneous solution is died out because of the exponential term, and the particular solution just continues on. So let's go and look at GeoGebra to see what these pictures look like. So that's the old one. Let me just switch there. So there's our solution curve. E to the minus 2x cosine x plus square root of 65 cosine 2x minus arctangent of 8. There's a little bit of stuff going on here at around t equals 0 and for negative times, but for positive times, it pretty quickly becomes just a cosine wave. So again, we can turn on the homogeneous solution. That's this blue curve. And the homogeneous solution, right, the way I graphed it, it oscillates a little bit, but e to the minus 2x just drives it down to 0 really, really quickly. Square root of 65 cosine 2x minus arctangent, that's this red curve. And you can see that the red curve ovalized the green curve pretty much by the time we've got to this point here, right? The red curve and the green curve are almost the same. So by the time we get to t equals 2, for example, we've certainly, the homogeneous solution has pretty much dropped to 0, and all we're seeing is the particular solution. So going back to the notes then, nope, that's not what I wanted to do. Let me go back to the sharing screen. There we go. So by t equals 2, more or less, great. So why is YH of t the transient? Why P of t is the steady state? The homogeneous equation has a negative exponent in it. And what does that mean? That means that as time goes on, it drops down to 0. And negative exponents, man, that drops down to 0 pretty quickly. By the time t equals 2, in both these examples, the homogeneous solution has gone away. Why P of t is just a pure cosine. It's a wave. And so it keeps its amplitude forever and ever and ever. So why does that happen? Here we have a mass on a spring with friction. So there's two responses. Oh, mass on a spring with friction being forced. So there's two responses, right? There's just the response of the spring to being put in motion, which is YH of t, of mass to being put in motion. And that dies out very quickly, just the natural response of the spring. Why P of t is the response of the mass to the forcing function. Right? And this persists. Right? And this dies out. So YH of t is the transient, YP of t is the steady state. Note that in this example, for example, our Forcing function has a frequency of 60, amplitude of 65, but the particular solution actually has an amplitude of square root of 65. Generally, the forcing function is going to lose a lot of energy to friction, and so the amplitude of the response of the spring is not going to be as large as the forcing amplitude. And the friction also gives you this phase shift because you're going to be, you have to overcome that friction. So same thing here, right? The forcing amplitude is amplitude of 10, but the response, the particular solution has an amplitude of square root of 2, right? What happens to the rest of the force that you're putting in there? Well, part of the force goes into overcoming friction, part of the force goes into the amplitude of the mass, and so that's why the amplitude of the mass is less than the amplitude of the forcing function. So particular solution and homogeneous solution are important concepts in this. The particular solution is the steady state. It's what you see after a very short time. The homogeneous solution is a transient. It dies out very quickly.